Chapter 10 Electrochemical Reactions Section 10.2 Thermodynamics of Electrochemical Reactions. The Nernst equation relates the Gibbs energy of reaction and the cell potential of an electrochemical cell. Delta G of R is the Gibbs energy of the reaction, or Gibbs energy change per mole reaction. N is the number of transferred electrons. F is the Faraday constant, 96,485 coulomb per mole. And E is the cell potential. This Faraday constant is simply the charge of one electron multiplied by the Avogadro constant. So it means 1 mole electrons has a charge of negative 96,485 coulombs. Now, what if all chemicals are in the standard state in the reaction? Well, then we simply put a superscript naught here and here. Now we have the standard Gibbs energy of reaction equal to negative NF E naught. E naught is the standard electrochemical cell potential. The Nernst equation can be used for half-cell reactions. For example, let's look at zinc-copper cell. We will also verify this. The standard Gibbs energy of reaction equals the standard Gibbs energy of the oxidation half-cell reaction plus the standard Gibbs energy of the reduction half-cell reaction. Now let's look at the anode. The half-cell reaction is this. From zinc to zinc 2+, 2 electrons are produced, the oxidation number increases. We have the standard oxidation half-cell potential 0.762. Now we can compute the standard Gibbs energy for this half-cell, which is negative NF times the standard half-cell potential. Plugging all the numbers, we get negative 147 kilojoule per mole. 1 coulomb times 1 volt is 1 joule. Now let's look at cathode, where reduction happens. The oxidation number of copper 2+ is reduced to 0. 2 electrons are transferred. The standard reduction potential is 0.337 volt. The standard Gibbs energy of this reduction half-cell reaction is negative NF reduction potential. Plugging all the numbers, we get negative 65 kilojoule per mole. We can also compute the total standard Gibbs energy of reaction for the entire electrochemical cell, which is this, negative NF E naught of the cell. Plug in the numbers, we get negative 212 kilojoule per mole. We can easily verify this negative 100 to 12 is the sum of the Gibbs energy of the oxidation reaction and the Gibbs energy of the reduction reaction. Now let's look at a different reaction over here. On the left hand side we have 2 iron 3, 1 iron 0. On the right hand side we have 3 iron 2. We will verify this again. We have the anode, in which this iron 0 becomes iron 2+. The oxidation number increases. We can look up the standard oxidation half-cell potential, 0.44 volt. 2 electrons are transferred, so we're plugging all the numbers, negative 85 kilojoule per mole. Now let's look at the cathode. We'll look at the cathode, make sure you have a reduction reaction, and make sure the oxidation number decreases. So we have this reaction. Oxidation number decreases from 3 to 2, and it's a reduction. But just to balance the number of transferred electrons, we see 2 electrons here, So sometimes we write the equation this way, so that 2 electrons are transferred. Now we have the standard reduction half cell potential, 0.77 volt. We can look up this kind of values. And then if we look at this second reaction, not the first one, the second one, with coefficients of 2, we plug in this 2 here, the number of transferred electrons, Faraday constant, reduction potential, we get negative 149. And finally we can compute the standard cell potential. We can compute the standard Gibbs energy of reaction given the standard cell potential. And what is that? It's this reduction potential 0.44 plus this 0.77. So plugging on the numbers, it's negative 2 electrons are transferred, we have Faraday constant, and we have the cell potential, we get negative 234 kilojoule per mole. And we can verify negative 85 plus negative 149 is negative 234. So we have this kind of reactions. Look, what if we divide all those coefficients by 2? And then we have only one iron 3 plus and 1/2 of iron atom. We get 1.5 iron 2. So it's right here. What about the standard cell potential of this? Well, it's the same as this reaction. It's still 0.44 plus 0.77, and the result is 1.21 volt. However, the standard Gibbs energy of reaction is halved to negative 117 kilojoule per mole. So this number is just 1/2 of this number, because in this reaction we do not have 2 transferred electrons. We have only 1 electron being transferred. This iron 3 plus gets 1 electron and it becomes iron 2 plus. And right here, this 0.5 iron loses 1 electron and become 0.5 iron 2. Now let's look at a completely different example. This time we will calculate the reduction potential of a half cell from iron 3 to iron 0. Iron 3 gets 3 electrons and become iron 0. The information provided to us includes the reduction potential of this from iron 3 to iron 2, and also another half cell reaction from iron 2 to iron 0. How do we tackle this problem? Well, because Gibbs energy is a state function, so we can actually decompose this reaction from iron 3 to iron 0 into this reaction and this reaction, and then we can combine these two. Now let's look at the first one. From iron 3 to iron 2, we have the standard reduction potential 0.77 volt. We can compute the standard Gibbs energy of this reduction reaction, which is negative NFE0 of reduction. 1 electron is transferred, so N is 1, Faraday constant. Over here, the standard reduction potential. We have another half cell reaction over here, also reduction. The reduction potential is negative 0.44 volt. And then we can compute the standard Gibbs energy of reduction. That's negative 2 times Faraday constant times negative 0.44 volt. Negative 2 comes from here. We have 2 electrons being transferred. Now this reaction is the target reaction, and this reaction is simply the sum of these 2 half cell reactions. And again, Gibbs energy is a state function, so we're going to just sum up this one and this one together. So this comes from iron 3 to iron 2. This is from iron 2 to iron 0. We sum it up, we combine the common factors, we get Faraday constant times 0.11 volt. You may compute the value of this, but it's unnecessary. We'll just have the standard Gibbs energy expressed this way. You will see why. Because the standard Gibbs energy of reduction for this reaction is negative 3F times the half cell this reduction potential. And then we can plug in the expression here. This guy is F, the Faraday constant, times 0.11 volt. And we have Faraday constant on the right hand side, so they cancel. The standard reduction potential is then simply 0.11 volt over -3, so we have this value here. And that's it. That's the reduction potential for this half cell reaction from iron 3 to iron 2. It may not be obvious, but we can also compute the reduction potential of this reaction as follows. So we have 3 electrons being transferred, so 3 times this reduction potential equals 1 times this reduction potential, because only 1 electron is transferred here, plus 2 times over here 2 electrons are transferred, so that's why 2 here. And then we can plug in all the numbers. Eventually we will get the same result. The standard reduction potential from iron 3 to iron 0 is negative 0.04 volt. So by looking at those examples, we learn that the half cell reduction potentials are not additive. I mean, although this reaction is the sum of these two reactions, but you do not just sum up these two voltages. You cannot do that. However, if you multiply the voltages by the corresponding numbers of electrons, well, you get products of potential and electrons, number of electrons or charges. Then the products become additive. The products are actually just proportional to the standard Gibbs energy of the reaction. The proportionality is the Faraday constant. And again, the Faraday constant is the charge of 1 mole electrons. Now let's look at the entropy change of an electrochemical reaction. So how do we do this? Well, first, dG is negative S dt plus VdP. So we have this equation. On a constant pressure condition, entropy is negative delta G over delta T. For a chemical reaction of physical change, we can use this same equation for the reactants and also for the products. And we take the difference between the two equations, one for reactants, one for products. And then we get this equation. The entropy of the reaction is equal to negative first derivative of the Gibbs energy of reaction with respect to temperature, as long as we hold pressure constant. And it's fairly easy to hold the pressure constant. Just do the chemical reaction under atmospheric pressure. Now, the Gibbs energy of reaction is negative Fe. Alright? So we replace delta G of R with negative Fe, and we have this equation. The entropy change of a reaction is NF times delta E over delta T under constant pressure condition. And E is the cell potential. So we simply used the Nernst equation from here to here. That's the Nernst equation. When all chemicals are in the standard state, we just add a naught in the superscript here and here. And now we have this standard entropy of reaction equals NF times the first derivative of the standard cell potential with respect to temperature. And sometimes if we just can measure the standard cell potential accurately at two different temperatures, we can just use the finite change of the cell potential on top, the finite change of the temperature on the bottom. We can just estimate the standard entropy of reaction. Or if we can measure the standard cell potential at various temperatures, we can make a plot. We have this versus temperature, and then we'll be able to calculate the standard enthalpy of reaction. First, we use the graph to determine the slope, which is the standard entropy of reaction divided by NF. And then of course the slope multiplied by NF will be this, the standard entropy of reaction. And finally we can compute the standard enthalpy of reaction. because H is G plus Ts. So delta H is delta G plus T delta S. Alright, and again, this is from the Nernst equation. The standard Gibbs energy of reaction is negative NF times the standard cell potential. N is the number of transferred electrons. F is the Faraday constant. Given this equation, the standard Gibbs energy of the reaction is negative NF standard cell potential. We can determine the equilibrium constant K of the electrochemical reaction given its standard potential. Why is that? Because the standard Gibbs energy of reaction is also equal to negative RT ln K. So we have this equation, and therefore the standard cell potential is RT ln K over NF from this equation, and ln K is simply NF standard cell potential over RT. Well, it does depend on temperature. You can see temperature is on the bottom right here. So what we can do is, at a given temperature, we can measure the standard cell potential, plug in those values, we get ln K. And then, of course, you can just get the value of K. Now here's one example for electrochemical reactions, such as this: zinc, copper 2 plus on the left, zinc 2 plus, and copper on the right. We have the standard, we have the Gibbs energy of reaction equals the standard Gibbs energy of reaction plus RT times ln Q. Q is the reaction quotient, and Q is, more accurately, the activity of zinc plus 2 plus over the activity of copper 2 plus. Of course, you can just replace this with the concentration of zinc 2 plus and the concentration of copper 2 plus. But remember, activity is the concentration multiplied by the activity coefficient. So if they have the same activity coefficient, you can simply replace A with the concentration. Otherwise, well, we need to take the activity coefficient into account. Fortunately, the activity coefficient typically just depends on the ionic strength. So somehow we can calculate the ionic strength, given the concentrations of the ions, and then from the ionic strength we can calculate the activity coefficients for both this zinc 2 plus in the anode side, and also we can compute the activity coefficient for copper 2 plus on the cathode side. And again, we're just assuming we have this, and then we replace the standard Gibbs energy of reaction with negative NF E naught. We replace the Gibbs energy of reaction with negative NF E. We have this equation, and of course, you can see we can simplify this equation by divide both sides of the equation by NF, actually negative NF. Now we divide both sides by negative NF. E is equal to E naught and then minus RT over NF times the logarithm of the activity of zinc 2 plus over the activity of copper 2 plus. Of course, the ratio between activities is equal to the ratio between the concentrations times the ratio between this activity coefficients. So fortunately, we can measure the concentrations, we can compute the activity coefficients given the ionic strengths, and that way we can establish a relationship between this cell potential and temperature. The cell potential decreases as the concentration of copper 2 plus decreases. So you can tell, if this decreases, this whole thing increases, and the logarithm increases, and because there's a negative sign here, this E decreases. What if the concentration of zinc 2 plus increases? Well, similar analysis. When this increases, this whole thing increases, the logarithm of this increases, and because of this negative sign, then cell potential decreases. Of course, the cell potential increases as this copper 2 plus increases, as this zinc 2 plus decreases. So not only we have this statement, we can also have a similar statement to describe when the cell potential increases. And finally, I just want to emphasize this E depends on T. So at different temperatures, you may have a different cell potential. I mean, even if everything else is the same, E depends on T. It's just because E depends on the Gibbs energy of reaction, and the Gibbs energy of the reaction does depend on temperature.